Okay, so when we break for the last class, we were looking into this configuration of biasing our MOSFET with a constant current source and having a provision of applying the incremental input also. And we said that we can simply do that by AC coupling the input. And we came up with some condition for which this V0 over Vi will behave approximately equal to GM times RDS, right? So what we wanted this contraption in a small signal sense to look like so in the small signal sense or in the incremental sense, we wanted this contraption to look like the one on the right. Okay. Okay, and for that we figured that there was a constraint. One of the constraint was if we find out what is the input impedance Rin, and we set Rin to be much greater than Rs, right? Then effectively for all practical purposes, the impedance looking in is infinite, that is much larger than Rs, which means Vg will be approximately equal to Vi. This is approximately equal to Vi if Rin is much greater than Rs. Okay, so then we concluded that if that is the case, if entire Vin falls appears at Vg, then naturally the current that will come through the transistor will be Gm times Vg. So which checks out, which is exactly what we want here. But there was another question that was raised that now this current will come in, will appear at this junction, and it has now two ways to go. It can go to the right into the RDS, or it can also go to the left into the RG, right? But if we want the contraption on the left to look like the contraption on the right, which means that our approximation should be such that no current flows through RG, or rather negligible current flows through RG. So if we have to figure that one out, what type of analysis would you want to do? Yeah, so but I mean, looking at the circuit, what type of analysis will give you that that estimate of whether the current prefers to go to towards RDS or into RG? Yeah, so essentially you'll have to figure out what does nodal analysis do. It essentially you'll have to figure out, looking into this node, if a current comes to this node, it has to decide whether to go to right or left, right? So essentially you want everything to go to the right, which essentially means that you have to figure out what is the impedance looking to the left and what is the impedance looking to the right, and the impedance looking to the left should be much higher, right? So how will you figure that out? So incrementally, if I sketch this and try to figure out the impedance, looking to the left is equivalent to saying that I am looking here and finding out R out. Okay. So whenever you have this transistor, you know that this is a voltage control current source. And if this is Vg, there will be a current of incrementally Gm times Vg. So what will be R out? Calculate R out and tell me. 1 plus GMRS. Yeah. Okay. Fine. So which one will be the? So I can approximate this further, right? So I can approximate this further and say that this is we already established that RG has to be much greater than RS, right? From the previous constraints. So which means that this is approximately equal to RG by GMRS. I neglect 1 plus. So this R out, this RG by GMRS has to be much greater than RDS. Right? So which means that RG should be much greater than GM times RS times RDS. And you see that this essentially is the same constraint that we arrived from the input side also. Now it's not necessary that always you will arrive at the same constraint. I mean, for this particular circuit, yes, but in some other cases you might have to do, the constraints might be different.
So to calculate this RO, we have ignored RDS.
Yeah. So I am comparing this impedance looking this side with RDS.
With RDS.
Right. So because ultimately, what is the purpose of doing it? It's like when you have to estimate what will be the current division at this junction. Okay.
Actually, I was thinking like RDS is inside this MOSFET.
No. So because RDS is actually inside the MOSFET. That's true. But I mean, when you are trying to figure out what is the constraint on RG, then you have to impose that. I mean, you have to do an appropriate analysis. Right? That's all it means. Okay. So any questions on any of this? Okay. So if you are satisfied, then let's do a quick swing limits.
So if you consider parasitics, then
which parasitics?
At the gate side.
Which parasitics at the gate side?
Gate to source, then there will be path to flow of current.
You mean the capacitance?
Yes.
Yeah, obviously. I mean, but we are not particularly bothered about those frequencies as of now, right? So obviously there will be path to flow, and that will have. In that case, also you will see that when you start calculating those parasitics, so you will see that this is no longer a first order circuit. Okay, so we'll get into those things later. I mean, after the midsem, right? So why are we doing all these things? So we are doing essentially all these things because we want an integrator, right? So when you say we want an integrator, what is meant by that? This is what we are essentially saying is that this is an error amplifier, and the output of this error amplifier is proportional to the input voltage times some proportionally constant, the current that is GM times VG. And I know that this I have to feed it to a capacitor to get an integrating action, right? So ultimately, at the end of the day, there will be a capacitor added here when you are putting it in the loop. Okay, so now this entire contraption makes it a first order circuit. But what he is pointing out is that we'll also have some capacitance here. Why there? We'll have a capacitance here. We'll have all sorts of capacitance connected to this between different nodes of this transistor. So then obviously it will not remain a first order circuit. Then you'll have to see that which one is the dominant capacitance, which one is setting the dominant pole, and so on, right? So those are the things we'll see in the later half of this course.
Sir,
yes.
Sir, can you please explain like your thought process, how you have approached? Like, sir, I was trying to find out this condition just by current division. Just I was like there will be two current, one will flow through RDS, another will flow through RG and RS.
Right.
And I was trying to find out that the current that is flowing through RDS is much greater than the current flowing through RG and RS.
Yeah, fine.
So in that case, it will become so complicated overall expression. But sir, you easily.
Yeah, so that's what I'm saying. I mean, so there are two ways of approaching a problem. You can do brute force and figure out what is the exact expression. You will get nice exact expression. But the thing is that sometimes in any design, you lose the crux of the problem in the detail. Okay, so what I am trying to motivate here is to figure out if you know exactly where the current has to flow through, all you need to know is the impedance of various directions. If you know the dominant impedance, when I say dominant impedance, I mean the lowest impedance path, the current will always try to escape in that direction. Right? So that's what we will do. I mean, that's what we are doing all through. KCL is essentially that. I mean, approximation of KCL is you figure out the lowest impedance path and ignore everything else. right? So which means that you have to be looking, you have to have the ability to look at the circuit and figure out the impedance at different nodes, right? So that's what I did, right? So I just essentially, even what I did here is an approximation. This is not exactly how it will function, but this will give you a estimate of what the circuit parameters need to be. So all I did was, I mean, it was okay when we did on the input side, right? You were fine, right? So Rin has to be much greater than RS. For the output side, I said that looking in that side should be much greater than RDS.
The last one.
Yes.
So, sir, if it was like that, this current GM
Right.
by addition, there is another factor that depends upon the some parameter through, like some current through the RDS. In that case, you would not apply this approximation, right?
No, I mean, it depends, right? I mean, then it becomes dependent on that. That's what the approximation is. You cannot really generalize, right? So the approximations are basically horses for courses. I mean, whatever is the condition, you figure out whether under that condition, this approximation holds true or not. Right? You cannot really say that this will go, this approximation you can take everywhere. Similarly, you cannot say that some approximation you took in some other circuit can be plugged in here. So that's totally not how it works. Okay. See, ultimately, I mean, if you think about it, this goes into the heart of of any design course. It's not very difficult to analyze, right? So none of these, if you know basic network theory, and I give you any of these, and I give you infinite time, all of you will be able to figure out what is V0 over Vi. What's the big deal? If you solve KCL and KVL, the entire electronic circuits is based on two equations, KCL and KVL. If you know how to solve mesh analysis, nodal analysis, done. Then why do you have so plethora of courses? It's not only about KCL, KVL, it's about how do you interpret those. Those are tools, right? Just like, I mean, if you having a calculator doesn't make you a good mathematician, right? So similarly, it's the same thing here. I mean, just knowing those two equations or just knowing how to run a simulator doesn't make you a good designer.
Intuition.
Yeah, so essentially, I mean, intuition is a very abused word, but yeah. So I mean, to figure out, so you need to be able to look at the circuit from different abstractions. So one is analysis, another is also breaking down a bigger problem into smaller parts and then figuring out how to analyze each of them. Okay, fine. So let's do the next part of it. Let's stick to this. Let me ignore this RDS for the time being. So I want to now figure out what is the swing limits of the input. That is, if assume that input is Vp sine omega naught t. You can assume RDS because without RDS you'll have infinite gain, then you'll have no swing. So input is Vp sine omega naught t. I want to figure out what is the maximum Vp that I can apply. So how will you go about approaching this?
You can find the gain.
We know already the gain, right? Small signal analysis, we figured out the gain. So your gain was how much? What is the relationship between Vi and V0? What did we make this circuit for? I mean, what is the expected output, expected gain? GMRDS, right? Minus GMRDS, right? So this expected gain is minus GMRDS times Vi is the incremental V0. So now what should we, how should I apply? How should I approach this to find out the swing limits?
Total gate voltage.
We have to, yeah, exactly. We have to first figure out what is the total gate voltage, what is the total drain voltage in terms of quiescent plus incremental. and then impose the condition. So what is the total gate voltage? Under the conditions that we have been able to, we satisfy all the constraints that we satisfied in the previous, finding out input impedance, output impedance, and all those things, we have satisfied the constraints. Then what, under those conditions, what is VG? Total gate voltage.
So VG equals to VP plus
VI, let's say VI plus
drain voltage.
Plus quiescent voltage at VG. Now quiescent voltage at VG and quiescent voltage at drain are identical, right? So this is VDQ. What is quiescent drain voltage? What is VDQ? In terms of the parameters that you know. I mean, you know threshold voltage, you know mu Cox, those things you know, right? So what will be VDQ? And obviously I naught is also known because you have used it to bias. How will you approach, if I ask you what is VDQ, how will you approach it? Yeah, right. So it's basically the good old saturation equation expressed in a different format. Threshold voltage plus under root 2 mu Cox W by L by I naught. Okay. So now, so if this is VDQ, then my total gate drain voltage is VD total is essentially V threshold plus under root 2 mu. Yeah, right. Thank you. Plus V naught, right? And V naught is in terms of VI, incremental output is minus GM RDS times VI. Okay, and total gate voltage is the same VDQ plus VI. Okay, so now what is the condition for maximum VI? Max. What will be the condition?
VG total greater VG.
Yeah, so when input increases, when VG increases, VD decreases, which means the transistor is trying to go into linear region. So we have to impose that condition, and that condition is VD total, that is VD in this case, should be greater than equal to VG total minus threshold voltage. Right, so which means that if you simply replace it, you get at the good old thing, right? So this is minus ds VI should be greater than VI minus, should be greater than VI, right? Because the other part is common. Yeah, something is wrong, right? Okay, minus VTH. Yeah, correct. Okay, so essentially your VP max becomes VTH by 1 plus GMRDS, approximately threshold voltage by GMRDS. Okay, so this is the upper limit. What is the lower limit? How will you figure out lower limit? You have to set the find out the total I naught and set it to 0, right? So what is total I naught that is flowing into? You can neglect RDS for this, right? So because that is an unnecessary distraction if when you are trying to figure out total I naught. Total, I should say ID in this case. So ID is equal to I naught plus GM VI. Okay. So this we set to 0. So you will get a max, I mean, VP min limit, right? So VP min limit will be I naught by GM. Okay, so this is actually pretty simple in this case. I mean, because ultimately it's essentially, I mean, another way of making a common source amplifier, and the constants of common source amplifier will also hold in this case. So before we move on from this architecture, any other question?
Sir, when it was absolute diode connected MOSFET, that means the RG was 0.
Right.
In that case, for any signal like input signal, the MOSFET never go to the diode region.
Right.
But
Yeah.
because of this RG, there is a possibility of
going
to the RG region.
Correct. Yes. And you would want that because ultimately you want gain, which means you don't want gate and drain to be shorted, right? Yeah.
There is no gain.
Yeah. Okay, fine. So, now if I take you back to one class back, why did we want to bias it with this current source? Why did we replace that resistor on top and bias it with the current source?
It was reducing gain.
It was reducing gain because for a fixed voltage, for a fixed VDD, we could only get so much gain, right? So as it turns out, there is one more reason why you would want to bias it with the current source, and that is as follows. So that has nothing to do with gain, that is to do with variation of parameters. So to explain what I mean by that, let me explain. So if you bias a transistor with a voltage source, right? So let's assume you have biased a transistor with a voltage source, right? You have applied a PGSCL, and you have, in other case, you have ensured that this current is constant. Fundamentally, there are two cases. One is you bias it with a constant VGS, or you bias it with a constant VDS, constant current. How you do it is a different matter, but fundamentally, these are the two ways of biasing. Now, if I concentrate on the bias of constant VGS, then my GM essentially is this. And if I bias it with constant current, so this is, write it down, this is. If I bias it with a constant current, my GM is okay. So now let's assume that your threshold voltage has changed for whatever reasons, right? Threshold voltage is dependent on many parameters which are outside our control. So if threshold voltage changes from VTH naught to, let's say, VTH plus delta VTH, how much will the GM change? So GM initially was, let's say, GM naught to, how much will it change? I mean, you simply apply VTH plus delta VTH in this equation. So what you will get? Right. So your GM will change from GM naught to minus delta VTH mu Cox W over L. Right. So this is essentially, I mean, I can express this in this format: delta VTH by VGS minus VTH, that is the overdrive, times, if I multiply the overdrive, and which essentially I'll get back GM naught. Okay. So if there is a change in threshold voltage, my GM changes by a certain factor. And that certain factor is essentially inversely proportional to the threshold voltage, inversely proportional to the overdrive. And that makes sense because if VGS minus VTH is very high, that is you have turned the transistor on with a lot of overdrive, then small change in threshold voltage wouldn't change this overdrive by any significant amount, right? So that's what is getting reflected in this equation. However, if I now focus on on the constant bias, current biasing situation, how much will GM change by? So GM goes from GM naught to no change, right? Because current is not changing, right? So there's no change. It remains at GM naught. Okay. So as you can see, there's a clear advantage, at least using the square law model of the MOSFET. Change in threshold voltage for a constant current bias circuit doesn't change your GM. Okay, so that's a good enough reason to use a constant bias, constant current bias. You can do the same thing for, what happens if, let's say, mobility changes, right? Again, mobility is beyond our control. It can change. So what happens if the mobility changes? In this case, if let's say mu goes from mu naught to mu naught plus delta mu, how much does the GM change? So GM goes from GM naught to mu Cox W over L V over drive plus delta mu Cox W over L V over drive, which is, this is GM naught plus delta mu by mu GM naught. Okay. Now we can do the same thing for this case. We can do the same thing for a constant bias case. So let me squeeze this in. If I do the same thing here, that is my mu went from mu naught to mu naught plus delta mu. My GM goes from, my new GM is essentially GM new is under root. Let me do it here because lack of space. Okay, so we can essentially use this approximation of, you can say this is 2 mu naught Cox W over L ID, right, times 1 plus delta mu by mu. So Taylor series of under root 1 plus x, where x is less than 1 is 1 plus half x. So we'll use that. So this becomes root. So this is original GM plus delta mu by 2 mu naught GM naught. So this variation is also better by a factor of 2. Right. So in both cases, we win by biasing your transistor with a constant current source with respect to desensitizing its parameter variations with respect to ambient conditions, right? Because it looks like with it's immune to threshold voltage variation, and it's also less sensitive to mobility variation. Okay, so that is one of the other reasons why in analog circuits we like to bias everything with constant current source. Mostly, I mean, it's not a mantra. I mean, there are cases where we need to bias with constant voltage source, but more often than not, you would like to bias with a constant current source. And I mean, even if you consider, if you don't consider MOSFET, if you consider BJT, in BJT also your GM is essentially proportional to I, right? IC in that case, right? So obviously in that case also you would like to bias with a constant current source because it's much more sensitive to change in current than even a MOSFET. Okay, any questions? So let me ask you a question then what is happening here? Why is, in principle, why is your GM insensitive to threshold voltage in constant current biasing? Same transistor, right?
Because here overdrive is not changing.
Which case overdrive is not changing?
So constant current bias.
Yeah. So what he is essentially saying is that how do you do a constant current bias? You do constant current bias. This is an example, right? So let's say your threshold voltage has changed. You have set your circuit like this and your threshold voltage has changed. Your threshold voltage, let's say, has increased by 50 millivolt. Then how will the circuit adjust itself? Because current is still I naught. So what will change? VG will change. VG will change by 50 millivolts, right? If the threshold voltage has increased by 50 millivolts, VG will also increase by 50 millivolts, thereby keeping the overdrives constant, right? So that's why your GM is not changing, right? But if you bias it with a constant voltage, then if threshold voltage changes, that directly appears as if the input has changed, right? So your GM will change. Okay, so that's essentially the crux of it. Okay, fine. So now that we are convinced that biasing with a constant current source is a better way to go about things, then let me take you back to one of the things that we discussed in the previous lecture, where how do you bias with constant current source? Using the method of negative feedback, you have options of sensing drain and feeding back the information at gate, or you can be sensing drain, feeding back the information at source, or you could sense the source, feedback the information at gate, or you could sense the source and feedback the information at source, right? These are the four possible combinations, and we already alluded to this one. There can be, I mean, let's do another one. Let's do the last one. I will see why I'm jumping to the last one soon. So when I say sensing at source, which by essentially what I mean is that the current source has been applied at the source. So the case that we did before this was current source was applied at the drain, but in this case, what we'll do, we'll try to bias using the current source at the source. Okay. So now now our purpose is to figure out how to ensure that the transistor is biased properly, right? How to bias the transistor properly and then apply incremental input. So now I took a transistor, I stuck a current source at the source, and I want to bias it using negative feedback. So what is the logic that I will go use to figure out what action is necessary? So I will look into this voltage, right? I look into the source voltage. And why am I looking into the source voltage? Because at the end of the day, I know there is this current. This is a voltage control current source. Transistor is a voltage control current source. Once biased in whatever fashion, it will be providing me some current ID. And the purpose of negative feedback is to ensure that ID equals I naught. So I have to do something to ensure that ID is equal to I naught. So now we have been doing the same thing multiple times. So how will I go about arguing it in my head? I'll be looking into this voltage, two current sources, right? So I'll be looking into this voltage, let's say V naught, or let me call it VS in this case, right? So if VS has increased, let's say VS is increased, what am I implying? No, VGS decreases is a different thing. I want to figure out what I need to VGS, but what is the conclusion if VS has increased? ID is more than I naught, which means I have to decrease ID. Right? And how do I decrease ID? I have to decrease VGS. Now, which essentially means that I have to do something which decreases the VGS, right? So how do I mean, do I need to do anything? the VGS is automatically getting decreased here, right? Because moment ID is increasing, VS is increasing, and thereby shutting down the VGS. So it looks like there is an inherent negative feedback that is taking place here. And this should not surprise you, because when we did this voltage control current source thing, which is independent of GM variation, I think 6 or 7 lectures back, we had something similar. And which essentially in that case, what we in that example, what we saw was, if this increases, I mean, if this increases, this also increases, right? And this contraption between the gate and the source behave like a source follower, right? So it was simply because there is an inherent negative feedback that is taking place. Okay. So now the question is that, I mean, just because I say that inherent negative feedback is taking place, I cannot leave the gate floating. I have to apply some voltage at the gate, right? So let's apply a voltage at the gate. What will be the required voltage at the gate to keep this transistor on? Yeah, so what will that be? In terms of I0 threshold voltage, blah, blah, what will that voltage on VG be? So this is VG. We are doing only quiescent now, right? If this is VG, what will be VS in terms of VG? Not only VG minus threshold, you have a current also, right? It will be VG minus threshold minus overdrive, right? So overdrive is minus okay. So this, and you want this VS to be at least greater than 0, right? Because I mean, even though ideal current source works across any voltage applied towards it, but we'll know that this ideal current, we will not have an ideal current source. This ideal current source will also be made using some transistor, right? So which means that VS cannot go below 0. So how much it will go is a different thing, but if there is a VS mean, in this case, let's assume it to be 0. If this is close to 0, which means that this has to be greater than, or rather VS mean. Let me just put it this way. Okay, so from there, you know what is VG mean. So VG mean should be greater than VS mean plus threshold plus V overdrive. V overdrive is, you know already what V overdrive should be. Okay, so now any questions?
So in this case, where we have to take the output?
We'll get to that. We have not applied the incremental input. This is only biasing picture, right? So we have to superimpose the incremental picture, because ultimately we want our incremental picture to look like this all the time, right? So this is, as I mean, I have not even shown what is at the drain, right? So as far as biasing it is concerned, I mean, does it matter if I connect the drain to directly the supply? It doesn't really matter, right? I mean, it's already biased. I mean, as long as the supply is greater than 1 threshold voltage below it, right? So it should not be a problem. Now, as you pointed out, that I need to figure out how to apply an input, and I have to take the output. So let's apply an input. Yes.
In the previous case, when I0 was in the drain side,
Huh.
in that case, if there was a DC volt or battery in the gate at that time, 2 independent sources was there. So 2 independent sources were trying to set the same current. But say in this case, because of VS, I mean the VS can adjust itself,
right,
such that
yeah.
the current can be set by I naught.
Exactly, right? So, okay, so since he raised the point, let me spend a couple of minutes on this. So what essentially his point was, it seems like we didn't have to do anything, the circuit biased itself. And why did the circuit magically bias itself is because from argument we just say that the Vs is going in the direction we actually want it to ensure that ID is equal to I naught, right? So which means that there is a negative feedback inbuilt into your MOSFET, right? So so from whatever we have learned till now, can we make sense of what this negative feedback is, right? So can we quantify that level of negative feedback, right? So one way to treat that is the fact that if I assume this MOSFET to be a, so incrementally this MOSFET is this, right? And let's assume that there is an R here. I neglected the R there, but let's assume there is R. This can be, I mean, the internal resistance of the current source or some explicit R that is there, but let's assume there is an R. This is PG. Yes. So now you see that this is actually when we define somebody that this is we define a contraption as a voltage controlled current source. This is not what that comes to mind. A pristine voltage controlled current source is this. You have two terminals at the input, VA, VB, and this current here is proportional to VA minus VB. Right? This is the classical definition of a voltage controlled current source. Okay, where with all the terminals marked. So now what essentially is happening here is, if you assume that this, let's assume that this is what you are playing with. You don't have the transistor, you are playing with this. Then what will you need to do to establish negative feedback? So then you will see that if this current, if this current is higher than the current that you are pulling out, then you have to increase VB, right? Because you want to decrease this current from the top, which means you have to increase VB. Does that make sense? Okay, so let me explain it another way. So you are arguing in your mind that I want to ensure the current, this current is equal to this current. Current from the top is equal to the current that is being dragged out. And let's assume that the current from the top is higher. So as somebody who is sitting in the lab and tweaking voltage sources at various terminals, what do you need to do? You want to decrease, and let's say you don't have any control on VA. VA is fixed. You have only control on VB. So what do you need to do? You need to increase or decrease VB? You need to increase VB, right? You need to increase VB. So source has increased, so you have to increase VB. Which means that you can simply achieve that by connecting these two. Right? So as it turns out, your transistor is wired in such a way that it is internally connected. Okay. So because you don't, it's a 3-terminal device with one terminal common between the input and the output. So this is your this is your transistor. So it's always internally connected and giving you that negative feedback in this configuration. Okay. So another way of if you want to look at it from the classical feedback mechanism, right? So if I have to look at it from this angle, right? So you have a current source. You want this to be GM VA minus VB. Okay, so let's say this is VA, this is VB. Okay. So now, essentially what this is doing is the mere connection of this transistor, the mere the existence of the, no, let me also connect this other R here because I have to draw the parallel. So what this transistor is essentially doing, that by its very build, these two terminals are connected. Okay, And this you can assume this to be shorted on the other side. It doesn't really matter. So this is VA minus VB. So this essentially is a negative feedback way of describing what your transistor is, the stuff in the black. Okay. So, and if you have to figure out what the, let's say the loop gain of this negative feedback loop is, what will you do? Break the, first you ground VA, break the loop anywhere, break the loop here. Let's assume you break the loop here, apply a test voltage, and figure out what the return voltage is, right? Yes, we return. And what will be that loop gain? Can somebody calculate? Somebody from the back? GMR, right? So loop gain is GMR, right? So from this also, again, I mean, we did this voltage control current source. This essentially was this voltage control current source, right? That we did few lectures back. And what was the gain between, what was the incremental gain between these two terminals? Okay, I'm probably confusing you. So now I am moving to the incremental model again. Okay. So let's assume this is R. This is shorted. You applied VI here. This is GM VI minus VS, or let's say V naught. So under the condition that you have negative feedback, what is H infinity between VI and V naught? 1. Okay. So now you know loop gain, you know H infinity. What will be V naught over VI? 1 times 1 by 1 plus GMR. So this becomes GMR by 1 plus GMR. So you essentially get back the same thing using a classic negative feedback mechanism. So I'm spending some time on this because this has an implication. I will get to that. Okay, so now let's get back to that. Get back to our total transistor model, or rather the quiescent plus incremental model. And you have a source, right? You have a source somewhere which you want to connect it to the gate. Okay. And ultimately, I would like to take the output from the drain because I want this incrementally to behave like a common source amplifier. Okay. So which means that let's concentrate on the drain side first. If I concentrate on the drain side, you will see that obviously I cannot short it to VDD because then drain doesn't move, my gain is 0. So we can do the same, this thing. You can apply an RL or RD or whatever you want to name and take the output from here. This we can do. Now, but I need to connect the input VI to the gate. So how can I connect it? Through a coupling capacitor, so I can connect it like this. Will this work?
But gain will be 0
Why?
because constant current will flow, so incremental change will not happen.
Okay, yeah, that's obviously one case. We'll get to the output side. But what about the input side? Is the input side behaving properly?
DC DC
So
source.
DC source
So
is
it's
directly connected to the
Yeah,
gate,
so
it
this,
cannot change.
the gate voltage cannot change, right? It's already connected. So then what should I do?
So do you have to connect the input to the gate, or you can also connect to the
If for this case, let's assume you connect it to the gate. Because we are essentially trying to make that incremental model of common source amplifier, right? I want to connect it to the gate, then what should I do?
So you can put this input in the series with this battery.
Yes, we can do. You can put VI in series with VG. That in fact you can do. But the issue is typically that in most batteries, both terminals will not be accessible. I mean, in a battery, both terminals are accessible. But when you have a incremental input, then incremental input doesn't come in terms of a voltage, explicit voltage source, right? So it can be a signal that is coming from the antenna. It can be a signal that is coming from the previous stage, where you don't have access to both terminals. You have access to only one terminal, and the other terminal is implicitly grounded. So then what do you do?
So gate setup VG such that incremental will not be zero. It's resistor divided.
Yeah, so the root cause here is that the DC source is directly getting connected to the gate. So which means that, I mean, as long as the DC source directly gets connected to the gate, you are lost. You are dead, right? Nothing can move. So you need to ensure that the DC source doesn't really play spoil sport, which means, I mean, one easy way to do it is put a resistor. Say RG. Okay. So that will ensure that your signal gets coupled here. So by the way, now tell me what is the constraint on, let's say, CC to ensure that my signal gets coupled properly.
RS plus CC combined impedance might be much less than RS.
Yeah. So I mean, so other thing is that's true, whatever you are saying. So other way of looking at it is essentially the fact that you have to ensure that at the signal frequencies, right? At the signal frequencies, the impedance looking here is much higher than the impedance looking to the other side. Okay. So which essentially is the same thing as you pointed out. The impedance of that is RS plus 1 over j omega c should be much lesser than that of RG. Okay. So from there you get the constraint on C. That's fine. Now actually the real question comes that whether you think if I connect it like this and take the final output from V naught, will this work? Will this circuit behave like incrementally? Will it behave like this incrementally? I saw some nodding of head. I mean, any comments? Yeah. Yeah, exactly, right? So it's a current source, it's an open circuit. Other way of looking at it is that this constant current is flowing through RL also, right? Because the constant current is flowing through the transistor, constant current is flowing through RL, which means V naught is stuck. V naught is stuck at VDD minus I naught RL. It cannot move. So if it cannot move, obviously my gain is 0. Okay, so then what should we do? Why is it not able to move? Yeah, that's true. That I naught is fixed, but in terms of gate and source voltages, fixed I naught means what?
So VGS is constant because source itself changing itself.
Correct, exactly, right? So when this voltage is changing, this voltage is also changing itself, right? So it's like a bootstrapping, is yanking together, right? So it's going in the same direction. So since it's going in the same direction, it's not allowing any change of current. So once you know the problem, the solution is easy, right? So you should not allow the source to move at signal frequencies. because you'd want this configuration for DC biasing. You want both to move in the same direction for DC, but you don't want the source to move for signal frequencies. Then what is the solution? You need to ensure that, I mean, it's almost equivalent to saying that this has to be constant bias, right? So it's almost equivalent to saying that I don't want the source to move, means that it's almost as if the source is biased with a constant voltage, right? But obviously it's not biased with a constant voltage. It's biased with a constant current, but a capacitor, a large enough capacitor acts as a battery, right? A large enough capacitor, if you push in incremental current into a very large capacitor, it doesn't really change its voltage. So I can have let's say C infinity. Here, if we have a C infinity here, which essentially means that at signal frequencies, your C infinity acts as a short, and your source is incrementally grounded. Now, if the source is incrementally grounded, then you kind of get back this architecture, but instead of RDS, you have RL. Okay. So what is but now, I mean, obviously you don't have C infinity, right? So what is the constraint on C infinity?
So impedance looking down to the current source must be very less.
The impedance looking means what? I mean, calculate and tell me. What is the constraint on C infinity for it to behave like a short at signal frequencies?
So 1 by GM should be very, very small compared to the impedance by C infinity.
Correct, right? As he said that, I mean, essentially the fact that other way of looking at it is you find out the time constant associated with that node, and then assume that the time constant is much larger than 1 over the signal frequency, right? So what is the time constant in this node? What is the time constant associated with this capacitor? Right, 1 by GM, because ultimately the impedance looking here is 1 over GM. So tau associated with C infinity is 1 over GM times C infinity. And this should be much less or much small? Much greater than the frequency of interest. And why? I mean, and intuitively, as you pointed out, one of the ways of thinking about it is the fact that you need to ensure that the C infinity, the impedance given by C infinity is much, or the C infinity acts as a short, which means that whatever impedance you are looking at, whatever impedance you are interested in at that particular node in which C infinity is connected, C infinity should give you the least amount of resistance, impedance, right? Which means that 1 over C infinity should be much smaller than 1 over GM. Right. So that's essentially the constraint. Okay. Any questions?
Sir?
Yes.
So can we put like this, the speed at which the C infinity is discharging is very high compared to the speed at which the signal is changing.
Meaning?
So the time constant tau C infinity is very, very greater than 1 by omega naught. So omega naught is high, means the input signal frequency is changing very rapidly.
Right.
So the discharge rate of C infinity is very, very greater than the speed at which the signal is changing.
Okay, so yeah, so I wouldn't say that it's a discharge rate per se, because there is having a large C infinity is equivalent to saying that you are not even changing the voltage on C infinity, right? So it's like if infinite capacity. I mean, if I take you back to the analogy of water, I mean, if this transistor to be a tap and water flow to be the current, then C infinity is a bucket.
It's a battery.
Right, it's a bucket. It's a huge bucket with a lot of water level, right? So you put in small drops of water, it doesn't really change the height. Right. So it's equivalent to that. C infinity is a capacitor which stores charge. If it's large enough, small amount of current change won't really change the voltage across it, right? So that's what is happening. I mean, what I mean, other way of looking at it is, it boils down to the heart of why a capacitance gives you large impedance at low frequency and low impedance at high frequency. It basically boils down to the fact that you are integrating a current, right? If this is, let's assume this is a low frequency current, and let's assume this is a high frequency current. This is I. This is I. So when you integrate this low frequency current intuitively, what do you get? You keep on integrating till here, right? I mean, you integrate all through, but you keep on accumulating charge for a longer period of time, right? So since you keep on accumulating charge for a longer period of time, you approach a large voltage. But for a high frequency input, you keep on accumulating charge for a low amount of time for the same amplitude, obviously. So you don't allow the voltage to build up. So hence the capacitor gives you low impedance at high frequencies and high impedance at low frequencies, right? It boils down to the integration operation. So that is essentially what we are leveraging here. At high frequencies, your capacitor voltage is not being allowed to change. And since the capacitor voltage is not being allowed to change, incrementally we call it to be source to be shorted. Okay. Okay, fine. So I'll not go through the swing limits conditions in this. I urge you to do it yourself. Let me go back to one more. So we did what? We did.
Sir,
Yes.
Here we find LS to be GMR, right? Better. Could you please go on? LS is turning out to be GMR.
Right.
If we apply V-test on top of R.
If we apply V-test on top of R, okay?
Then GMR is coming, right?
You can apply anywhere, right? You can apply it here. You can apply V-test here.
So if we apply after the summer.
If we apply here, okay.
So loop gain will come out to be GMR.
No, right? No, if you apply, why should it come out? You are breaking the loop, right? This is, you are assuming this to be a 4-terminal device again, right? These are not internally connected. If you connect that internally, then what you are saying is right. So what I did, I tried to make a transistor using this 4-terminal 2-port.
No, actually, I was asking like if we apply the V-test at gate, sir.
Yeah. So I think I get what you are saying. What he is essentially trying to say is that if I apply the voltage here and I find out the voltage here, right? So it's GMR by 1 plus GMR, right? Exactly, right? So, but what is this? When you apply when you apply it here and observe here, you are not breaking the loop because the loop is connected internally, right? So loop is connected through this. Okay, so in order to break the loop, during analysis, you'll have to assume this to be a 4-terminal device and then do. So, okay, let me then, good question. I was planning to address this at the end of the class, but let me address it right away. So last class, I think some of you mentioned that in one of the assignment problems, I think this was this one. If you find out the H infinity H naught and use the formula, you get a different result with respect if you find out V naught over Vi, right? Anybody else also got this? Which is actually correct, because what essentially is happening here is you have multiple loops, which is not particularly evident, but now it should be evident to you because this is in itself a feedback. Okay, so that H infinity and all those formulae are true when you can express it in this format. Right? If you have a single loop, then you break one loop and you use that formula, it works. But if you have multiple loops, that formula doesn't work as is. There needs to be some correction to it, and we'll not get into that. So that is why, I mean, I have been avoiding return ratio. One of the reasons is that with return ratio, you get exactly what you want, what you need. I mean, when you do this analysis using return ratio, you get exact output. You don't get any approximation. But return ratio is not very intuitive. And so, however, in circuit design, we would like to go for intuition. So we will not get into that return ratio concept. So we'll just stick to the fact that even though your loop gain analysis might not give you exact V naught over Vi under closed form, but it's still accurate enough, and we'll stick to that. Okay. Okay. So let's move to the other one. Yes.
So the extra term that was coming, we were not able to get VO by VI and
Right.
by this method equal. So the problem I identified was that there was implicit feedback there.
Yeah, exactly.
Like GM was pulling out the current from R to parallel C.
Yeah, so I mean, if you now consider this to be a 4-terminal device and you break it, so now so if you are interested, you can try this out. So VI, and you don't assume this transistor to be a 3-terminal device. You assume it to be a 4-terminal device, where the other terminal is here. Okay, so let's say this is VB. So you call this GM VI minus VB. And you assume that the negative feedback is connected here. Okay.
Now we can break the loop from VB.
Yeah, exactly. Right. So now, I mean, obviously you have to ground this VI, and you can break the loop here, and then you find out what is the loop gain. But now, because if you break it at VB, the entire loop gets broken. But earlier, if we had broken it here or here or here, this internal loop was not getting broken. So that's why you can end up in some situations where the closed loop V naught over Vi is not exactly what you want. Okay, but if you break it here, you will get. But I mean, since we will be dealing with transistors all the time, and it's not physically possible to remove the source from this 4th terminal, so we'll ignore this. We'll just say that it still works. There will be some error, but as long as that error is not dominant, we don't really bother. And I'm sure you found out that the error term that you got was much less than the other terms, right? It doesn't really matter.
So if we break the loop, we don't consider it 4-terminal device, then applying V-test is a kind of messy. I mean, it also yanking that node is better. I mean, we apply voltage source, so it starts delivering the current.
Right.
So we don't know, like a GM is pulling current from R to parallel C.
No, that I quite didn't understand. What do you mean by that?
Like if we break it like that, we take out
apply
V-test, then it's okay. Like V-test won't be supplying any current.
Correct.
It won't be
Yeah.
affecting our circuit.
Right.
If we break it the other point,
right,
and apply the V-test, then V-test starts giving the current, and
right,
we are
right.
not able to see that.
But then you'll have to use the loading. You have to have the loading reflected to the other side. Right. So that's what essentially is the loading, right? When V-test is pulling current, which means when it was connected in feedback, whatever was connected in the feedback to the return path was also supplying current. But you have taken it out by disconnecting the node physically. But that is not an accurate representation of what the loading of the return path was. So you have to put that load back, right? So that's why if you broke it here, let's say you break it here, then you have to put back this 1 by GM. Right? Because looking up here, the impedance is 1 by GM. Okay. So as it turns out, there are multiple ways of analyzing feedback networks, and each one of them have their pros and cons. And return ratio, I haven't talked about return ratio in detail, but if you are interested, if you want to look up, you will see that return ratio gives you exact output, but it's at the expense of figuring out what is the level of feedback, amount of feedback, where can you apply and how can you stabilize the circuit, and so on and so forth. So, so most circuit design courses and most circuit designers, that's why stick to this loop gain thing, even though it is slightly more erroneous. Okay, so we are out of time. I'll not start the other part right now. Any questions? No? Okay, fine.